Okay, we're going to continue discussing graphics with showing Matlab examples. And this time, instead of plotting functions defined analytically, that is in terms of a formula, we're going to be looking at plotting graphics that come from data. And the example we're going to use is one that I'm more familiar with, but it could be anything. We're going to be plotting temperature, salinity, and density data collected in the ocean off the coast of Florida. So it's part of the Go Ship program. They do these hydrographic sections where the ship crosses the basin and they stop at regular intervals and lower an instrument off the side of the ship to collect some data. And so we'll be looking at that. So to give you a little bit of idea what the situation is for collecting the data, if this is the vertical axis Z and gravity is pointing downwards and this is the sea surface, then there'll be a ship cruising along the ocean, and they have a winch and a cable that lowers over the side of the ship, and there's an instrument with these bottles and a sensor on it, and they can send an electrical current down the wire, a signal that will close the bottles at regular intervals. And there's also an instrument called a CTD, which is a conductivity. The C stands for conductivity, the T stands for temperature, and the D stands for depth, and it's really measuring the pressure, but there's a very close relationship, nearly linear relationship between depth and pressure in the ocean. So the instrument goes down, and this would be the bottom of the ocean, and they collect data and they can make profiles of temperature as a function of depth or as a function of pressure, or salinity, which you get from the conductivity. So salinity is a function of conductivity, and you can get it by measuring the conductivity, and you can make plots of conductivity as a function of depth. And I guess the interesting thing for the purpose of this example is that while it is true that temperature is a function of depth and salinity is a function of depth, temperature is not a function of salinity, and salinity is not a function of temperature. So these are independent variables, or they're both dependent on depth. All right, so let me show you the data that we want to look at. So over here, I have what's called a TS diagram, and the points along the scatter here, this is one such profile collected in the Atlantic, and the vertical axis is the temperature, or what's called the conservative temperature. It's very closely related to what we used to call the potential temperature, or the potential temperature in the atmosphere. And it's the temperature, it's kind of a conservative quantity that measures the energy content of the fluid parcel, in a sense. I guess the reason is you want the conservative temperature corrects for the fact that if you move a water parcel up and down in the water column, there are differences in pressure, and the pressure will cause if you push it downwards, the pressure will increase, and that will cause the fluid parcel to have more internal energy, and that's due to the work done on the parcel by the environment. Conversely, if you bring the water parcel up, it will expand and do work on the environment, and its temperature will drop. So if you bring it downwards, its temperature will increase because of the work done by the surrounding on the fluid parcel, and if you bring it up, it will expand and lose energy. And so the conservative temperature tries to take into account these effects. And then the x-axis is what's called the absolute salinity, and it is the mass of dissolved solids per kilogram of seawater. And the absolute salinity is different than what is measured. What is measured is the practical salinity, which comes from the conductivity. So to go from the practical salinity to the absolute salinity, it's important to know where you are in the ocean, because the composition of the salts in the ocean, while they're fairly constant, they do vary a little bit, and those variations will cause some slight differences in the corresponding mass of dissolved solids per kilogram of seawater. Anyways, there's a thermodynamic equation of state for seawater that you can download and use in Matlab, and you can compute these various relationships from typical hydrographic data. So the scatter of points is what was measured, and so each point has a temperature and a salinity. It also has a pressure, which is not shown in the diagram, and it has a sigma naught value, which is shown by finding out along which contour intersects the data point. So for example, the point over here, this point right at the intersection would have a sigma naught value. Oh, I haven't told you what the contours are, but would have a density which is around 1,027 kilograms per cubic meter. So what is plotted in the contours are what's known as sigma naught, which is the density a fluid parcel would have if it was brought up adiabatically from its depth at its pressure up to the sea surface. And that's what the contours are showing. So you can see up here, we're near the sea surface, the temperature is high and the density is lower, and as we go down the profile that was measured, at first the salinity increases, then the salinity decreases, and also the density tends to increase. We cross these sigma naught values of increasing sigma naught, and the temperature decreases. We go down the water column, it's colder at depth. So the sigma naught value, which is the contours, is a function of conservative temperature and salinity as well as pressure. Whereas the potential temperature is not a function of the absolute salinity the way you are usually used to when you see graphs. The x-axis is the independent variable and the y-axis is the dependent variable. In this case, both the x and the y-axis are the independent variables, and the contours are the dependent variables. All right, so but it is true though that while temperature and salinity are not functions of each other, both are functions of depth, and I will show you such a graph. Here's one where we have plotted vertical profiles of temperature, salinity, and density, in situ density, as a function of the depth. And the depth is obtained from the pressure and the latitude of the water parcel. So if we know those, we can convert pressure to depth. So in a general rule of thumb is that every every meter you go down in the water column, the pressure increases by 1 decibar. So every 10 meters, you get an extra atmosphere of pressure. And so in this case, what we have is the potential temperature is a function of the depth. So we've broken two of the conventions that we might be used to. One is that the dependent variable is along the x-axis, and the independent variable, the depth, is along the y-axis. And another rule we've broken is that the y-axis is increasing downwards as opposed to upwards. And we do that, we break all these conventions to make the data easier to understand, because we usually like to think of gravity pointing downwards, and we're used to orienting our graphs such that downwards is pointing towards the bottom of the paper. Another thing we see in this figure is the absolute salinity, which was computed from the measured variables, and the in situ density, which was also computed from the measured variables. And there's 3 different axes which are labeled with their symbols and their units along the x-axis, and the vertical axis is always depth, and I didn't bother showing them on the other 2 panels to remove some clutter because they're the same. So this is 6,000 meters across all the panels, and you can maybe see faintly in the background there are these grid lines that can help you know which this is the 4,000 meter grid line. So we'll see how to make this plot in a little bit. I want to show you another plot. It's a zoom in of the variables in the top 1,000 meters, which is known as the thermocline in the ocean. And we still have depth going from 0 to 1,000 meters. We still have the potential temperature and the absolute salinity. Those are the same. In this case, we plotted the sigma naught value. which is the density the fluid parcel would have if it was brought up to the surface adiabatically. And we subtract 1,000 kilograms per cubic meter to have numbers in a more reasonable range. So it's just something to remember. The density of fresh water is about 1,000 kilograms per meters cube under normal conditions. And so we just subtract 1,000 off. Now the interesting thing that I wanted to point out about this graph is if you look as you go down into the water column, the temperature is decreasing, and that will lead to an increase in density. So in general, density decreases with increasing temperature. So if you, I don't know if I just said it right, but if you decrease the temperature, the density goes up, and you do see this going on. It's also true that if you increase the pressure, the density goes up. So that's also part of the reason why the previous graph, the in situ density, increases here is because of the increase pressure. But in this graph, the sigma naught is corrected for the effects of pressure, because this is the density the water would have if it was brought up adiabatically to the surface where the pressure is. So all these are reference to the same surface pressure. The salinity, on the other hand, well, just like the temperature, decreases with depth. However, the density will tend to decrease with decreasing salinity, whereas the density increases with decreasing temperature. And this led Stommel to point out this interesting fact, this interesting curiosity called an oceanographic curiosity, or the perpetual salt fountain. And the idea is that if you imagine sitting a tube into the ocean and you were to pump water up the tube at first to just kind of prime the pump, then the water in the tube would have the salinity of the deeper ocean. So let's say you have a tube that extends from the surface down to 1 kilometer, 1,000 meters. You pump up the water. Now the water in the tube will have the salinity of the 1,000 meter water, which is generally lower than anywhere else above it. You can see that from the graph, right? The salinity is lower down here than it is as you go up. And if you have a tube, it will be impermeable to the diffusion of salt into and out of the water. But the tube will not prevent the heat from conducting from the inside or the outside of the fluid parcel, the tube. And so what will happen is that the water inside the tube will become, will equilibrate to the ambient temperature of the surrounding water. And now what you will have at a fixed depth will be water that has the temperature, the same temperature as the surrounding waters, but the salinity of the deeper waters, which is much less. And so that water will be more buoyant than its surrounding, and then therefore it will be accelerated upwards. And so once you've set it up, the water will keep flowing up the tube and sucking water up to the surface. So they actually did some experiments in the lab, some small scale experiments where they had, they tried to describe the diagram here, showing this salt fountain where they have dyed, fresher water below, and in the white region, I think that it corresponds to saltier, warmer water. And once they prime the pump and let it go, then the dyed water is sucked up the tube and fills up the top of the apparatus. I think that's the way it works. We'll revisit this this example maybe later in the course, if we can set up a mathematical model to describe the perpetual salt fountain. They point out in the paper that it's unlikely that this would be a useful way of extracting energy from the ocean, but they claim that it could be where it might have some applications in bringing up deep waters that are richer in nutrient up to the surface for aquaculture or something like that. Anyways, it's an interesting phenomena. So right now we're going to go to Matlab, and we are going to make these plots that I've shown you. And first I have the browser open at the goship.org website. So you click the data directory, and then we have CTD and bottle data. There's also some other kinds of data. We will click on the bottle data, CTD and bottle data, and then we can choose the basin we want. We're looking for data from the Atlantic Ocean. And then they show you all the cruise tracks that are available. The one that I downloaded was this A05 section, which is highlighted in yellow, that crosses the Atlantic, goes from, I think, from Florida to the Canary Islands or something like that. the Azores maybe. And if you click that one, then you have the option of downloading what is either netcdf data or CSV data, comma separated values. So I downloaded the netcdf data, and I've already done that. And I'll show you where that is. If I'm in my directory in this ESS212 lecture 1, and if I created a subdirectory called A05, I think, and then in there are all the netcdf files for all the different stations. And I think the station that we looked at last time, or that we were looking at, is the one for CAS 60. So I'll copy and paste this in my text editor so that we can assign this name to a variable. So the variable is a string, is a Matlab string, and it contains the name of the file that I want to read. And if I want to see what's inside that file, there is a command in Matlab called ncinfo that will return the information about a particular netcdf file. And so if I run it, where am I? CD. Alright, so this example 2, oh yeah, it's in a subdirectory. So I need to put the path correctly, A05. So since I'm in the directory I'm in right now, the current directory, or the working directory, is this one in lecture 1, and I need to go into the subdirectory A05 where the data is. So now the data is in one level lower. Okay, so let's run it, ex2, and fname is the name of the file. H is this handle that returns the info for this particular file, and you'll see there's H is a structure and has variables as one of the attributes, or one of them fields. So if I do h.variables, I can find out what the variables are, and there's one called variables.name, and I get the names of all the variables. So if I scroll up, you could see all the particular variables in this file. There's a pressure QC is a quality control, temperature quality control, salinity quality control, oxygen, and so on. There's the time that the CAS was taken, the latitude, the longitude. And so now we can read in each of those variables using the command ncread. So we'll read the data in. So read in the measured variables. Alright, so I read the temperature, the practical salinity, and the pressure, and I guess I need the longitude and the latitude. ncread fname lon lat. Oh, it's called longitude. Alright, and then lat. So it's at 24.5 degrees north, and the longitude is at minus 62 or 62 degrees east. 62.5 degrees east is where this particular CAS was taken. Okay, so this read in the measured variables. Then we're going to have some computed variables. So we're trying to make this plot, remember? We have the data, and we're going to try to make this TS diagram. And so we will need to compute the absolute salinity down here, or the conservative temperature, and the absolute salinity. And for that, we use the thermodynamic equation of state for seawater, and that's also available from the internet, from the web. So if I go to the TEOS10 website, TEOS10, then you can download, well, let me just Google it so you can see how I get there. TEOS10 takes me to the home page, and then if I go to software, then there are these options for downloading. There's some instructions, installation instructions, that tell you the steps, and you can download it for different languages: Matlab, Fortran, C, C++, Julia. I don't know, this must be Python, maybe, I'm not sure, PHP. And you install it, and it's pretty straightforward to install. So I've already done that, and all the functions for the equation of state are prefixed by a GSW. So if I do help GSW row, then it tells me what the GSW row function does. So you have to know the names. There is this little memory card that explains the different variables, kind of like a little summary of them all, and you can print it out. You can download and print it out, and it has the names of all the variables in the toolbox. And so row is the one that computes the density. It tells you what the inputs are, so it needs absolute salinity and conservative temperature and pressure, for example. And there's some more descriptions of what the units are of all the inputs and outputs and the references. So we will use those. So right, so the ones we want for this graph are the absolute salinity and the conservative temperature. So absolute salinity, SA, is equal to GSW SA from SP, I think that's what it's called. Let's look. Help GSW SA from SP. Yes, that is the name of the routine. And the inputs are the practical salinity, pressure, longitude, latitude. SP, pressure, long, lat. And again, the reason we need the longitude and latitude is because the toolbox has some information about the slight variations in the composition of seawater, in the particular chemical composition of the salts in space. And so that to get a very accurate conversion of conductivity or practical salinity into the mass of the solids, you need to know where you are in the ocean. I mean, it's for very small corrections, but the toolbox does use them. And then the conservative temperature, GSW CT from T. And I can't remember the inputs, so help GSW CT from T. And the inputs are SA, T, and P. And we can also get the depth, so Z is equal to GSW help GSW C from P. Yes. Pressure and latitude. So pressure and latitude. We want to compute the density, rho GSW, rho SA, CT, and P, I think. Help GSW sigma 0 is another one we'll use. And sigma 0 SACT. All right. Sigma 0. Oh, an error. Z from P. If I plot like this, it plots, all the points are connected by line segments. So for example, if I zoom in, this is not really a scatter plot, right? All the points are all connected by lines. So what I want to do is add a symbol, and then now if I zoom, you will see that they really are points. Right? It really does plot the individual points. And so that's what we'll use. So make the plot. So figure 1, plot SACT make the font bigger so we can see. And then label, put the labels, I guess, so we know it's what X label, S sub A. So to do with the subscript, you do an underscore, and grams per kilograms. And then the Y label. And for the Greek letters, you can start with a backslash, and then you type in the name. If you want a capital letter, you start with a capital So I want a capital theta. So I put a capital T theta with a backslash. And then the units, which are in degree C. So the degree, to get a superscript, I use the little hat, C. All right, so this looks a lot like this graph. One thing that's missing is the contours that I have in the back. So these are contours of sigma 0. And so I will try to compute, or I will compute, sigma zeros to put on the background for these contours. Now, what I've computed so far are only the sigma 0 values for the points along this array of points here, along these individual discrete points. But if I want to make the contours, I need to compute sigma rho for each and everywhere on this field, on this 2D array. So what I will do is create a 2D array of salinity and temperature points, and then compute sigma naught for each one of these points, and then make the contours. So let's do that now. So we'll start by doing, before we plot the discrete points, the scatter. So for the x-axis, we go from 34 in steps of, let's say, 0.1 all the way up to 37.5. And for the y-axis, we go from 0 to 25. That's in steps of 1 to 25. And then to make the 2D mesh, I do mesh grid. That's a Matlab command, equals mesh grid xy. So let's run it and I'll show you what these xy's are like. So example 2, x. So x is a size of x, is a row of points. Y, size of y, is also a row of points. But size of x is a 2D array, and size of y is a 2D array. And what it does is it just copies, for each y value there's a row of x values, and for each x values there's a column of y values. So if I try to contour it, for example, contour x, y, and x, then let me do it with the F so you can see. Color bar. So the x increases in this direction, and it's the same for every y. Right, it goes from low to high. And if I do the same command, then now with y, now I'm contouring over y values, and the y's are increasing in this direction. So what I want to do is compute sigma naught for each and every one of these x and y arrays. So sigma 0 is equal to GSW sigma 0. And then I want to put in the salinity, which are the x values, and the y values, which are the conservative temperatures. And I want to stick those in the same 2D array, so I'll first define sigma 0 to be a 2D array of zeros of the same size as the big X. So this will initialize sigma 0 to be a 2D array, and then I will assign the points individual values according to what the x and y sigma naught values are. And then I can do the contour. Contour x, y, sigma 0 in K for black contours. And then if I want to label, well, let's just try this and show you step by step. Oh, I need to do a hold on if I want to see it. Hold. Otherwise, the plot command will overwrite the contours. Right, so this is starting to look like this graph. You see the array of points, you see the contours. Now I'd like to label the contours, and I can do that by grabbing the handles from the contour command and then doing the labels. C-label, CSHH, font size 16. Right, so now we have these labels for the sigma naught value, the density values in the map. And then I would like to have the grid on, and then let's print the figure, print -d, and then device, and then you get to choose what kind of file you want, JPEG, PDF, TIFF. You can do help print, and it tells you what are the options to to print it, I think. In this case is ts.eps. So this is the name of the file. It'll be ts.eps, and then the format to save it in, it'll be a encapsulated PostScript color. So let's try it again. EX2. This is my figure, ts.eps. And that is the saved PDF file. Oh, it's actually, did I do P? It's saved that as a PDF, converted to a PDF. That's my Mac did this in preview. I guess I could keep the points in blue. I don't like the red, so let's change the reds to blue. So over here, I can force it to put blue points. Yeah, like that. All right, so that's figure 1. And then let's do figure 2, which was these vertical profiles. And for that, we just make what are called subplots. So this will be a panel with 3 columns and 1 row. And so for that, we do it as follows. So figure 2, subplot 1, 3, 1. That will be the first figure, so that will be the conservative temperature. Subplot 1, 3, 2 will be the panel for the absolute salinity. Subplot 1, 3, 3 will be the density. And then I plot, well, let's see, what shall I plot? Figure 2, CLF, plot Z versus conservative temperature. All right, so this is the Z-axis, and this is the conservative temperature going from 0 to 25. So if we want, it always wants to do the dependent variable along this axis, but we want the dependent variable along this axis, right along here. So all we have to do is just interchange the order of the CT and the Z. So if I change CT versus Z, and then set the line width, set GCA font size 60, not the line width, the font size, I mean. Let's try it. CLF. Right, and now the first panel is this graph. And then for the second panel, plot, that is supposed to be absolute salinity versus Z, set GCA font size. And the last one is the density, plot rho versus Z. Alright, so let's make the lines thicker, add the grid marks and the labels. Alright, so H is equal to set H line width 2. So let's add the grid lines. Grid on. Right, so what we need, the other thing is to add the Y label and remove those negative marks. So for the first panel, we're going to add the Y label depth in meters. And for the other ones, we will set, we don't need the Y labels. We'll reset the tick marks, the tick labels. So set GCA Y tick label. I think that's what it's called get GCA. It is called Y tick label. Yeah, Y tick label. So let's do that. 6,000, 5,000, 4,000, 3,000, 2,000, 1,000, 0. I don't know if that works. Let's try it. Right. And then for the other ones, we'll just remove these tick marks. So set for the other ones. Set y GCA y tick label, and just put an empty box. And same thing for the last one. Good. And then what else do we want to do? We can add more tick labels around here and over here. Put the spacing every 5 degrees if we want. So let's do that. So the first one here, set GCA X tick, and the ticks will go in steps of 5. 0 degrees by steps of 5 up to 30. And then the next one, we go from 35 to 37.5. Set GCA X tick from 35 in steps of 0.5 all the way up to 37.5. And then the last one, we go in steps of 10. Set GCA X tick 1020 in steps of 10 to 1060. Example 2. Oops, something is wrong. X tick. Right. So these look pretty similar, right? This is the 3 graphs. This is this one. I think they're pretty much the same. Here I didn't go all the way up to 37.5. So for this, to force it to go all the way up to the last one, the trouble is the last point didn't show up, and Matlab tries to resize the x and the y axes automatically. If I want to force it, I can do over here axis, and then I put the range of x values, which will go from 35 to 37.5. And I think that will force it to be correct. Nope, that did not work. Oh, I need to put the y values also. So for their minus 6,000 to 0. Yes, there we go. So I think that's a fairly faithful representation of what I had before. And then figure 3 was this one, where I only went all the way down to 1,000 meters. And so let's, and I plotted the last panel with sigma naught instead of rho. So remember, this one is rho, which has the pressure dependence. This one is sigma naught, which uses the conservative temperature, which is already taken into account the fact that the temperature will change if you move up and down adiabatically. So let's, first of all, just copy what I've done for figure 2. For what I now call figure 3. And the last panel, which used to be rho, will now be sigma 0. And I will now change this axis command. Where was that axis? This one. To only 1,000 meters. And I will add this to the last one. But I must change the range from 24 up to 28. And the first panel, I need to do the same thing. but the x range is from 0 to 30. 0 to 30. And this should be 1,000. Did I change this to 1,000? 1,000. Alright, so something's wrong with the row range. So that's panel 3. I guess one thing right away that's easy to fix, what I call row is no longer row. That's sigma 0. And then the tick marks. Oh, the tick marks I need to change. I had them set before, so I wanted to go from 24 up to 28. But notice that's going to be kind of crowded. Oh, I do it in steps of 0.5. 0.5, but I only label every other tick, right? I label 24, 25. So for that, you first set the ticks at every half interval, but then you have to set the labels. So set GCA X tick label, and then I put the values I want, which will be 24, nothing, 25, nothing, 26, nothing, 27, nothing, and 28. So then I separate them by commas. So 24, 25, 26, I forgot a tick mark. That looks good. Close the parenthesis and run it. Example 2. Oh, the tick marks are too many. These now start at 1,000. I want to go from 1,000 by steps of 200, right? So the next one is 800, 600, 400, 200. Set GCA Y tick, and we start at 1,000. We go in steps of 200 all the way up to the surface. So it's very tricky here. You have to make sure that if you're going to reset the labels, that you set it correctly. Otherwise, Matlab will just recycle them. So it goes from 1,000 to 0, and then it ran out of tick marks, tick labels, so it recycled. So you can get nonsense as tick labels. So you have to be sure that you set your tick marks where you want them to be, and then you label them correctly. Otherwise you can get crazy plots. So I think it'll be right now. No, they're totally wrong. Oh, it's because it's minus 1,000. Yes, okay. So it goes from minus 1,000, but that's depth of 1,000. I've relabeled it to be 1,800 and so on instead of minus 800. And that's that. All right, I think that's everything for this example of plotting data, plotting functions that are defined in terms of data, as opposed to what we did in the first video where we plotted functions that were defined in terms of formulas, defined analytically. We also plotted something that was not a function, the scatter plot of the temperature and salinity. We also plotted the sigma naught contours, and that is a function, but it's a function of 2 variables instead of just 1. So for every conservative temperature and every absolute salinity value, we have a unique sigma naught value. So we did these plots. In the next segment of the video, we'll do more plots of different types of fields.